Nobel laureate who says that with steady improvement in the um, fabrication technique, Van der Waals heterostructure promise a new gold rush rather than graphene aftershock. The wide choice of materials with various electronic properties enable Van der Waals heterostructures to have high technical potential that cannot be achieved by common semiconductor heterostructures. The development of the graphene-containing nanostructures based on alumina and zirconia will extend the raw material range for creation new composites for a large number of human activity. The hybrid structures consisting of nanocrystallites with the graphene sheets are recognized as the most effective for a lot of relevant materials. They can be used to produce supercapacitors, protective coatings, high-speed cutting tools, electrodes for lithium-ion batteries, and so on. The main problem is obtaining oxygen-free graphene sheets with low degree of agglomeration. And in the composite, graphene often agglomerate. It leads to microcracks, bubbles, separations, and anisotropic distribution. So the thoroughly studied process of homogenization and reinforcement of graphene composites are necessary to ensure uniform distribution of compounds in the material without the appearance of oxygen-containing defects in the graphene. And about the synthesis process. Among acceptable methods, wet methods were recognized as most preferred due to the low operating temperature, environment friendliness, simplicity of technical implementation, and good reproducibility. We have considered an approach to synthesis of hybrid structure. It involved 6 steps: obtaining of graphene suspension, preparation of salt aqua solution, the formation zone, mixing zone, and graphene suspension, gelation and heat treatment and 500 degrees. Here you can see two powder. This is the real picture of the graphene alumina and graphene zirconia nanopowders. The process of obtaining graphene suspension involves 3 steps: exfoliation, dispersion, and stabilization of the resulting suspension. The transparent graphene colloid was obtained in which presence of suspension graphene sheets was confirmed using Tyndall effect. And the EELS analysis show that there is no graphene oxide in the obtained graphene. This peak at the 500 electron volts corresponding to the oxygen do not appear in the spectrum. The figure C describes the mechanism of the for formation of the graphene sheet and the fixation on the organic molecule surface. Well, and about the composite powders. From the left hand, you can see a pure alumina powder. The average size is 410 nanometers. The size of aluminum oxide crystallate incorporated into graphene sheets doesn't exceed 3 nanometers. The dark field picture suggests that the surface of the agglomerates is coated with 1 or 2 layers of graphene. The specific surface of the composite was 155, which is 1.5 times more than for the pure aluminum oxide. According to the X-ray data, The composite powder, after heat treatment at 500 degrees, was fully crystallized and consisted from alumina in the modification monoclinic with spinel impurity. The calculated average size of alumina crystallines was 3-4 nanometers for the monoclinic modification and 10-12 for spinel impurity. There is no 3D carbon phase. The next figure shows the diffractograms for the synthesized composite calcinated at 900 degrees and gamma aluminium oxide. We see that increase in heat treatment leads to formation of ultra-dispersed gamma aluminium oxide with the calculated crystal size 3-4 nanometers. So the heat treatment don't give up in increasing the size of the crystallines. And the last picture showing the overlay of diffractogram of composite and fullerene C60. The comparison shows that fullerene-like structure may be particularly contained in the composite. And about the zirconia nanopowders. The powder consists mainly of mesoporous agglomerates with size 400 nanometers, formed by crystallines with size 10-20. And metaporous, there are about 3-4 nanometers. The zirconia crystallines are discretely incorporated into graphene layers almost uniformly. The figure C describes the inclusions that size is 2-4 nanometers. There are no mesoporous in the composite. When we use light fraction over the graphene, its layers block the mesoporous as a membranes. The comparison of X-ray patterns of the composite and pure zirconia shows that crystallization is difficult in the presence of the graphene sheets. It shows that the composite zirconia is present as a monoclinic tetrahedral modification and not stoichiometric phase. The same peaks we can see in the pure nanopowder or obtained nanopowder of zirconia obtained from the same zirconia containing zone. However, the ratio of them is different. We have a increase in non-stoichiometric phase. So we think that the zone particles are isolated between the graphene sheets as a nanoreactors, where zone gel transition occurs. The resulting gel is also bound to the graphene sheets. During the suspension calcination, an organic-inorganic complex is destroyed and crystallization takes place directly on the graphene. So graphene saves its unique electronic properties, and at the same time it fixes on the composite in the composite heat structure. And now about the rheology. The rheology properties were tested on the mechanical testing machine. At the beginning, we took exact weight of the powder, placed it in the stream. Then, on the mechanical testing machine, we can conduct the experiment. At least 5 measurements were carried out for each composite. Then the values were averaged and calculations were made using the formulas of deformation, compressibility modulus, and compressibility coefficient. Here you can see a typical deformation stress curve based on 5 independent numerate experience for both powders. Using mathematical apparatus, we can divide the curves into three steps. The first one is a linear section, second polynomial, and exponential. Since the alumina oxide particles have a nanoscale size, it becomes energetically benefit that the shape becomes close to the bone. So the first stage of the rheology curves is limited to the deformation value up to 20-27% and is accompanied by a linear increase in stress and deformation, which occurs due to the powder particles move into the pores. Here, the process keeps Hooke's law of elastic deformation. The second stage corresponds to deformation from 20 to 45%. It's agreed to a very steep nonlinear rise in stress with increasing of deformation. The particles movement is due to the accommodation or adaptation of them among themselves, and from the other hand, due to the deformation of their volume. In the third stage, when the stress is increased over the wide range, a small changes in the deformation occurs. The compaction process is carried out mainly due to the growth of the contact surface during the particles deformation. Let's look to the in stage. Let's draw a trend line. The tangent of the inclination angle is equal to the modulus of compressibility. So the larger angle is, the greater elasticity of the powder. We see that introduction lower than 2%, if talking exactly 107% weight percent of graphene leads to increase in the elasticity of the powder more than 2 times. Well, let's turn back to the whole code here. What we see in the following 2 stages: the pure alumina is alumina. The middle section is much longer than it is for the composite powder. The particles still have a lot of space to adapt and take place that is more convenient from the energy point of view and compact as much as possible. The deformation curve is 2 times larger for a pure alumina than for the composite, as graphene sheets inhibit adaptation. If we compare the first section of the both process, we see that the angle of the inclinations is different from them. We assume that this is due to the elasticity of the graphene sheets. Graphene plays role of the nanosprings that the material has some elasticity that can be deformed more at this stage than pure oxide, which after occupying all voids, activity resists compaction. It turns out that it is the third stage that is determined in the process of forming hybrid structures with increased impact toughness. The curves for the composite with zirconia oxides are presented here. Let's compare the rheology curves for the both oxides. Of course, the particle size, shapes, and nature of the powder affect on the curves. However, in both cases, a similar tendency is observed for the effect of graphene sheets on the rheology. At the inside stage, the slope of the curves increases and the compressibility modulus is 2 times larger than for the composite. Than for a pure oxide, I'm sorry. And below you can see the calculated constants for the oxides and composites. In conclusion, I would like to say that the process methods for the synthesis of graphene ceramic composites opens up new possibilities to increase functional materials with new properties. The development methods of the powders, synthesizing, ensuring uniform distribution of graphene sheets in the composites in volume and in increased uh, dispersion of aluminium and zirconia oxide compounds. Even though graphene containing causes significant changes in the rheological properties of the nanostructures composite powder and leads to decrease in the compressibility. The elasticity of the obtained model ceramic materials increased with which make it promising for the development of the fine-grained materials with improved mechanical properties such as hardness and fractional stress at low contact.